Welcome to College Algebra. My name is Gregory Carlson. This is 3.6 Part 2, the last new notes before the midterm. So that's some good news. So let's look at a few actual real-life examples of using direct variation and inverse variation. So this is actually really cool. This is like a mystery of the universe type thing. We all know that everything has gravity, and every object exerts gravity on every other object. So the Earth exerts gravity on me, this pencil exerts a little bit of gravity on myself, and I attract the pencil towards me, but our masses are so small that we can't really detect that over short time scales. But it's true that every single particle exerts gravity on each other, and there's actually a formula for it. The universal law of gravity states that the force of gravity between two objects varies directly with the product of their masses and inversely proportional to the square of the distance between them. So the equation is this. The force of gravity is equal to, and um, it's a very, so it's directly proportional to the product of the masses. So it's mass 1 times mass 2. That's the mass of the pencil and the mass of me. And inversely proportional to the square of their distances, or d squared. And you notice we're missing our constant of variation. And so in this equation, we call that number g. So there you go. There's the formula for the force of gravity between any two objects. And what's really cool is Newton, Sir Isaac Newton, a famous mathematician and physicist, figured out that if we just looked at two really big objects like the moon and the earth and looked at the distance between them, we could detect this force based on their orbits, and we could actually solve for g. So we can figure out what this actual constant of variation is. And it's a really small number. I don't know exactly what the number is. I'll put it in the description. But what's interesting about this number is whoever created the universe, whether it was God or whether it is a programmer or whether it's just natural forces, this number right here means something. This number is very special. It wouldn't work, our universe wouldn't work if you changed this number. And there's about 20 or so of these constants of the universe. There's the electromagnetic constant, there's the gravitational constant, there's the mass of the electron, there's the mass of the proton. All of these different values, the weak magnetic force, the weak force, the strong force, all of these numbers are very, very fine-tuned. And if you changed even one of them, we'd be living in a universe with very different properties, very different gravity, very different electricity. Maybe those things wouldn't even exist. In fact, if you change the mass of an electron by just a little bit, stars wouldn't be able to form, and none of us would even exist. So what's really cool is I think of whoever made the universe as being a programmer, and this value was put into the code of the universe to make it all work the way it works like it does. It's really a neat thing to think about. So anyway, so that's your mystery of the universe as it relates to direct and indirect variation. Let's look at whatever you believe, this number and the other constants are very special. In fact, what some mathematicians and physicists are trying to do is come up with equations that relate all of them together. Because if you could relate all of the, Einstein was working on this, Albert Einstein, if you could relate all of the constants of variation of the universe, you would basically have a single formula that explains the entire universe. So that would be really cool. All right, let's look at another one. The ideal gas law states that the pressure of an ideal gas varies directly with its amount, N, the ideal gas constant, R, the temperature, T, but inversely to volume. So write the equation. So the pressure of an ideal gas varies directly with the amount. The ideal gas constant, I should have written that first actually, because that's the constant of variation. So that's the constant variation is R. And that'll be different depending on what type of gas it is. Different gases have different constants. We're varying directly with N. directly with T, but inversely with V. So there's the ideal gas law. If you're just looking at an ideal gas, you might recognize this if you've taken physics. Normally the formula is PV equals nRT, but since we've solved for P, we see that the formula has been arranged for P. So as R, the amount of gas or temperature increases, the pressure of a gas on a container increases. But as the volume increases, that pressure goes down, so it's inversely related. 2 more to go. Volume is equal to 4/3 pi r cubed is the formula for the volume of a sphere with radius r. How does V relate to r? So we see that V is here. 4/3 pi is kind of like a constant of variation. And we see that r is to the 3rd power. So what we would write is, because r is on top with V, we would write V varies directly, not with r, but with the cube of r, because it's r cubed. So you could either say with r cubed or with the cube of r. So that's how V varies. It varies directly with the cube of r. Last problem. Here's another application. The force of wind blowing on a wall varies jointly as the area of the surface and the square of the velocity. So in other words, jointly means that it's direct variation with both values. That's what varying jointly with something means. So we've got the force of a wind. It varies jointly as the area and the square of the velocity. So let's write that down. The force is going to equal to jointly with the area and with the square of the velocity. And can you see what I've left off? That's right, I've left off my constant of variation. By the way, in this equation, remember r was the constant of variation, so we didn't need a k in that one. All right, and we didn't need a k here because g was the k. Okay, so there's the formula. Let's clean this formula up a little bit. So there's our formula. As the surface area of a wall increases, the force of wind on that wall goes up, and the square of the velocity. The faster the wind, the more force is on the wall. So if a wind of 60 miles an hour exerts a force of 20 pounds on a surface of 1/5 square feet, how much force will 180 miles per hour place on a surface of 130 square feet? So let's calculate it. We have a force of 20. First, we need to solve for k. So we have a force of 20 pounds is the result of 1/5 of a square foot. So we put 1/5 here, times our velocity, which was 60 miles per hour. And that number is going to be squared. Now, in all of these problems, it's really important not to mix up your x's and y's when you're doing these. Make sure you stick with the complete system each time and don't be mixing in that other number. So when we're doing this problem, it's really important that the 20, the 5th, and the 60 all come from this system. Don't be mixing in these other numbers, okay? That'll lead to a mistake. So let's solve for k. We have k over 5 times 3,600, because 60 times 60 is 3,600. Let's do 3,600 divided by 5 to cancel these. So 3,600 divided by 5 is equal to 720. So I get 20 is equal to 720 times k, right? Do you see how I did that? That became 720. So I have 20 equals 720k. Divide both sides by 720. Boop, boop. So k is equal to, and I'm going to go ahead and turn this into a decimal. 20 divided by 720. 0.02778. So there's my constant of variation right there. So now I want to know, to wrap this up, how much force will 180 mile per hour wind place on a surface of 130? So again, we updated our equation, which is now F equals 0.2 778 times the area times the velocity squared. So let's figure out this new force. Our new area is 130 square feet, and our new velocity is 180 miles per hour, and that number should be squared. So multiply all these numbers together, and we're done. So let's do it. We have 180 squared times 130 times 0.02778. That is a huge force. That force is 117,009 pounds of pressure, 0.36. That is an incredible force right there. That's amazing. So you could see how this would be used in real life. Let's say you're an engineer or a contractor in Florida where they have hurricanes. And so in the lab, you do a test to see how wind and how the surface area work together to create force on a little piece of material that you have in the lab. And that material would determine what this K is. Then you would know if a hurricane hit with 180 miles per hour winds, you know what kind of force would be on that wall, so you know what kind of materials you have to make so that it could withstand that, and what kind of support it would have so that you could withstand that kind of force. So direct and inverse variation have wide-ranging applications to all sorts of different types of things, including the nature of the universe. I hope you've enjoyed this semester so far of college algebra. We've reached the halfway mark of the class. If you have any questions, please leave them in the description. And if you like this video, please like and subscribe. And very good. I hope you study hard, and I hope you do well on the midterm. If you've watched all these videos, done all the homework, and studied, there's no reason why you shouldn't do well. So I will see you after the midterm. I might do a review session video, maybe. And I will see you for Chapter 4. Thanks so much for watching. This is Gregory Carlson, and I will see you later.